Welcome to AI Frontiers, a synthesis of recent research. In today's episode, we'll be exploring cutting-edge developments in machine learning published on May 12, 2025. This synthesis brings together 17 research papers from the computer science machine learning category, offering a comprehensive look at where artificial intelligence research is heading. Throughout this podcast, we'll analyze major themes emerging from these papers, examine groundbreaking findings, and take deep dives into some of the most influential works in this collection. Machine learning continues to drive innovation across numerous domains including healthcare, finance, transportation, and entertainment. The papers we'll discuss today showcase both the diversity and depth of current research in this rapidly evolving field. Machine learning represents a fundamental paradigm shift in computing, developing algorithms that learn from data without explicit programming. The current landscape spans multiple approaches. Supervised learning trains models on labeled examples, unsupervised learning identifies patterns in unlabeled data, and reinforcement learning enables agents to learn through environmental interaction. Deep learning, utilizing neural networks with multiple layers, has powered recent breakthroughs, particularly in computer vision and natural language processing. The field faces several key challenges: improving computational efficiency as models grow larger, ensuring fairness across demographic groups, enhancing model interpretability for critical applications, and developing techniques that learn effectively from limited data. These challenges are being addressed through rapidly evolving architectures and training techniques that push the boundaries of what's possible with machine learning systems. The first major research theme identified across these papers focuses on geometric and manifold learning, which explores how to effectively model the intrinsic structure of high-dimensional data. This approach leverages the manifold hypothesis, the theory that high-dimensional real-world data typically lies on or near low-dimensional nonlinear manifolds. Diepeveen and colleagues present significant work combining normalizing flows with Riemannian geometry preservation techniques. Their innovative approach enables better clustering, dimensionality reduction, and interpolation by maintaining geometric properties across the learning manifold. This represents a substantial extension to traditional manifold learning approaches by incorporating normalizing flows, a powerful framework that allows for more flexible and accurate modeling of complex, multimodal data distributions. The integration of geometric principles with generative demonstrates how mathematical foundations can directly enhance machine learning performance on complex data structures. Privacy-preserving machine learning emerges as the second major research theme, addressing the critical need to protect sensitive data while maintaining model performance. As machine learning applications proliferate in domains like healthcare and finance, privacy concerns become increasingly important. Cotorobai and collaborators introduce a federated random forest solution that enables multiple institutions to collaboratively train tree-based models without sharing raw data. This addresses a significant gap in federated learning frameworks, which have primarily focused on gradient-based models like neural networks. In parallel, Zhang and colleagues developed FairZK, a zero-knowledge proof system, allowing model owners to demonstrate the fairness of their algorithms without revealing proprietary model parameters. This innovation effectively balances the need for transparency with intellectual property protection. Together, these approaches reflect growing concern about privacy in machine learning while offering practical solutions for deploying models in privacy-sensitive contexts. The third major research theme centers on fairness and ethical AI, focusing on ensuring machine learning systems make equitable decisions across different demographic groups. Arcolezi and collaborators investigate a critical tension between privacy-enhancing technologies and algorithmic fairness in their paper, Fair Play for Individuals, Foul Play for Groups. Their rigorous analysis reveals that anonymization techniques designed to protect individual privacy can significantly degrade group fairness metrics across demographic categories. This highlights a fundamental challenge in designing systems that simultaneously protect privacy and ensure equitable outcomes. Diepeveen and colleagues develop a theoretical framework using Shapley values for explaining reinforcement learning decisions, addressing the black box nature of complex models. These papers demonstrate a growing focus on both technical solutions and theoretical frameworks for ethical AI. The research highlights the need for multi-objective optimization approaches that can balance competing ethical considerations in ensuring learning system design. Computational efficiency stands as the fourth major research theme, with researchers addressing the substantial computational demands of modern machine learning systems. Papers in this category focus on reducing training time, memory usage, and inference costs through various innovative approaches. These include novel pruning techniques that remove unnecessary connections in neural networks, quantization methods that reduce numerical precision without sacrificing accuracy, and architecture optimizations that streamline model structure. These advances are particularly critical for enabling deployment on resource-constrained devices and environments, such as mobile phones, edge devices, and regions with limited computational infrastructure. The research in this area proves essential for democratizing access to advanced machine learning capabilities, ensuring that state-of-the-art AI isn't limited to organizations with massive computational resources. By making models more efficient, researchers are expanding the potential applications and accessibility of machine learning technologies across diverse settings. Analyzing these 17 papers reveals several critical insights and breakthroughs across the research landscape. First, geometric understanding significantly improves model performance on complex data structures, with manifold learning approaches demonstrating superior results on multimodal and non-Euclidean data. Second, privacy and fairness objectives can conflict in fundamental ways, requiring careful trade-off analysis when designing systems for sensitive applications. Researchers quantify these trade-offs and propose frameworks for balancing competing objectives. Third, federated approaches are expanding beyond neural networks to include tree-based models, broadening the applicability of privacy-preserving techniques. Fourth, zero-knowledge proofs are emerging as powerful tools for verifiable machine learning, allowing model properties to be certified without revealing sensitive details. Finally, explainability techniques are becoming increasingly sophisticated for complex models, with new methods that can interpret decisions from reinforcement learning agents and other advanced architectures. These findings collectively push forward the boundaries of what's possible in machine learning. Across these research papers, several methodological approaches recur, highlighting common techniques and frameworks in contemporary machine learning research. Most papers combine theoretical analysis with empirical validation on benchmark datasets, ensuring both mathematical rigor and practical relevance. Multi-institutional collaboration features prominently in privacy-preserving algorithm development, bringing together expertise from various domains to solve complex problems. Ablation studies, systematically removing or modifying individual components, help researchers identify the contribution of specific elements within complex systems. Comparative evaluation against state-of-the-art baselines prompts for understanding advances, with standardized metrics enabling fair comparison. Real-world case studies frequently complement synthetic experiments, demonstrating how techniques perform under authentic conditions with natural data distributions and constraints. These methodological commonalities reflect the magical research practices in machine learning, emphasizing reproducibility, comparative analysis, and practical application. Let's examine our first selected paper in more detail. Manifold Learning with Normalizing Flows by Diepeveen and colleagues. This work combines normalizing flows, a class of generative models that transform simple distributions into complex ones through a series of invertible transformations. With techniques that preserve Riemannian geometry, the paper addresses a fundamental challenge in machine learning: effectively learning from and modeling multimodal data with complex underlying structure. The authors develop a novel architecture that maintains geometric properties throughout the flow transformations, ensuring that distances and relationships between data points remain meaningful in the transformed space. This approach demonstrates significant improvements in downstream tasks, including clustering, interpolation between examples, and generative modeling. What distinguishes this paper is its elegant integration of geometric principles with powerful generative models, providing both theoretical guarantees and practical implementation details. The authors rigorously prove convergence properties, while also delivering code that practitioners can immediately apply. Our second selected paper, Federated Random Forest Solution, by Cotorobai and colleagues, enables collaborative training of tree-based models without requiring participants to share raw data. This work addresses a critical gap in the federated learning literature, which has predominantly focused on neural network architectures that can be trained with gradient-based methods. The authors develop a secure protocol for distributed decision tree construction that maintains performance comparable to centralized training, while providing formal privacy guarantees. The approach uses cryptographic techniques to securely evaluate split criteria across distributed datasets without revealing individual records. Particularly noteworthy is the system's practical efficiency. The authors demonstrate deployment in a healthcare consortium, where multiple hospitals collaboratively trained predictive models while complying with data protection regulations. This opens new possibilities for privacy-preserving analytics in sensitive domains, allowing organizations to benefit from machine learning without compromising data confidentiality or regulatory compliance. The third selected paper, Fair Play for Individuals, Foul Play for Groups by Arcolezi and colleagues, investigates the tension between privacy-enhancing technologies and algorithmic fairness. This work stands out for its rigorous analysis of a fundamental trade-off in ethical AI development. The authors systematically quantify how various anonymization techniques, including differential privacy, k-anonymity, and synthetic data generation, impact group fairness metrics across different demographic categories and machine learning tasks. Their findings reveal that stronger privacy protections often led to less equitable outcomes across groups, creating a challenging dilemma for system designers. The paper proposes a novel framework for balancing these competing objectives, introducing a multi-objective optimization approach that allows practitioners to make informed decisions about appropriate trade-offs for specific applications. This research highlights the need for interdisciplinary approaches to AI ethics, drawing on perspectives from computer science, law, philosophy, and social science to develop comprehensive solutions that address both privacy and fairness concerns. Looking toward the future, several promising research directions emerge from the current landscape. First, there's growing interest in unified frameworks that integrate privacy, fairness, and efficiency objectives, allowing system designers to make informed trade-offs between competing goals. Second, geometric deep learning approaches for complex, structured data types show significant potential, particularly for graph-structured data, 3D shapes, and other non-Euclidean information. Third, federated learning systems for non-neural network architectures represent an expanding frontier, with recent work on decision trees likely to inspire similar approaches for other algorithms. Fourth, zero-knowledge verification systems for model properties beyond fairness could enable transparent auditing of various aspects, including robustness, stability, and compliance with regulatory requirements. Finally, explainability techniques for increasingly complex model architectures remain critical as systems become sophisticated and are deployed in high-stakes domains. These directions suggest a future where machine learning systems become simultaneously more powerful, trustworthy, and aligned with human values. This synthesis of machine learning research was created using multiple AI technologies working in concert. The content analysis and text generation were performed using GPT Anthropic CLAUDE-3-7-SONNET-20250219, providing comprehensive coverage of the research papers. Text-to-speech synthesis was conducted using DeepGram technology, converting the written analysis into natural-sounding narration. Visual elements accompanying this podcast were generated using Grok image generation capabilities, creating informative visualizations of key concepts. While these AI systems enabled efficient processing of complex research content, human expert review was essential for ensuring accuracy and coherence. This review process verified technical details, confirmed proper representation of research findings, and ensured balanced coverage across papers. Despite careful review, some oversights may exist in this synthesis. All references to original papers are provided in the companion materials to this podcast, allowing listeners to explore topics of interest in greater depth and verify information directly from primary sources. Subscribe to AI Frontiers to receive weekly research syntheses and analysis covering the latest developments in machine learning. By joining our community of AI researchers and enthusiasts, you'll gain insights into cutting-edge techniques and applications across the field. We encourage you to comment with research topics you'd like us to cover in future episodes. Your input helps shape our content. Share these podcasts with colleagues interested in machine learning advances to spread knowledge throughout your professional network. Visit ifrontiers.com for additional resources, including full references, code repositories, and extended discussions of the papers covered in our podcasts. Our website also features interactive visualizations of key concepts and searchable archives of past episodes, organized by research theme.